Okay, good morning, welcome to
FamilyMath1152.
FamilyMath1152. So today we're going to go through a really neat proof I saw about the square root of 2 being irrational. But I think you might already know a proof of why the square root of 2 is irrational. So to kind of get going today, I thought maybe I'd have you go through that proof. Do you know a proof?
I think so, yeah.
Okay, well, how would you prove it?
So it's a proof by contradiction. So you assume that the square root of 2 is rational at first, and thus it could be written a over b, where a and b are in lowest terms, and a over b equals root 2.
Okay. Alright, so we have a fraction, a over b. So this is what we're assuming.
Yep.
That it's rational. That's the opposite of being irrational. Okay, good. So that means it's ratio of 2 integers.
Yep.
Which we can put in lowest terms.
Okay, so we square both sides now, and so we get a squared over b squared equals 2.
Okay.
Now we're going to multiply both sides by b squared, so we get a squared equals 2b squared. And now we know, since we're multiplying b squared by 2 and it equals a squared, we know a squared is even. And from that we can tell that a is also even, because if it's a this has to be an integer, and so you'd have to have 4 in the factorization of a squared.
Okay, so yeah, so that's very good. So you can write a as even, let's call it 2m.
Okay,
So now this side is 4m squared.
Yep. So we get 2m squared, so 4m squared, equals 2b squared. Then we can divide by 2 on both sides, so we get 2m squared equals b squared. And now from the same logic, we know, since we're multiplying by 2 on this side, b squared has to be even, and so b also has to be even.
Okay.
And now we've proved that both a and b are even, so we can call b equal to 2n. And we thought our fraction a over b was in lowest terms, but now we can divide the numerator and denominator by 2 and write it as m over n.
Okay.
And we can repeat this process with m over n as well, because we didn't specify exact numbers for a over b, so we can do this infinitely many times. And since you can't really do that, that's just gonna lead to nowhere, basically.
Yeah, so you assumed in the beginning that they were in lowest terms, and it turned out that was impossible.
Yeah.
But you're also correct. You can just keep repeating the process, which always divides both numbers by 2, and you're left with an integer.
Yep.
And why can't you do that infinitely often?
Well, I mean, you'd end up with infinity over infinity, basically.
Well, now you're dividing by 2.
Yeah.
Well, you'd be starting with infinity over
You'd
infinity.
be starting with infinity over infinity to begin with, and if you start with a finite number, you can't do this anymore.
Right. Eventually, you'll have. No finite number has infinitely many 2's in it.
Yep.
Okay. All right, that's really nice, and that's a good proof with a lot of neat ideas in it. But we're going to look at a new proof today, so let me bring that one in.